Everything you remember about yesterday is, according to physics, less likely than the version in which yesterday never happened. Not possibly less likely, less likely. That falls out of a theorem Ludwig Boltzmann proved in 1872, a theorem still taught to first-year students, still printed in the opening chapters of every book on heat. Everyone assumes it says entropy grows toward the future. Read the thing closely and it says something else. It says entropy grows in both directions. And in December of 2025, 3 physicists published a formal analysis showing that your belief in the past is a choice, not a result. If that moved something under your feet, hit like and subscribe, because it gets worse in a very specific and very well documented way. And leave me one memory in the comments. One you are completely certain is real. You will want it later. Screen face down. We start at the top and we go all the way down. Start with something you have never once doubted in your life. Drop a cup on a tile floor and it breaks. It does not unbreak. Nobody in the history of the species has watched shards jump off a floor, gather into a rim, and settle back onto a saucer. Pour milk into black coffee and it clouds, swirls, and blends into brown. It never separates back out while you sit there watching. Your coffee cools toward the temperature of the room. The room never gives the heat back. This is the second law of thermodynamics. It is the most reliable statement in all of science. Physicists trust it more than they trust almost anything else they know. If a new theory turns out to contradict it, the theory is what gets thrown away, and nobody argues very hard about that. Here is why it works, in the simplest way anyone has found to say it. Take a fresh deck of cards, still sealed, still in factory order, ace through king, suit by suit. Now shuffle it. You know what happens. The order is gone, and it does not come back, no matter how long you keep shuffling. But the deck is not seeking chaos. The deck has no preferences at all. The cards are just moving. The reason order vanishes is that there is almost nothing in the room that counts as order, and almost everything in the room counts as mess. There is exactly one factory arrangement. The number of shuffled arrangements is so large that if every human who ever lived had spent their whole life shuffling, we would not have scratched the surface of the list. So a shuffle takes you from the tiny corner of the possibilities to the vast open middle of them, every single time, without any law forcing it to. That is entropy, not a substance, a count. It tallies how many microscopic arrangements would look identical to you from the outside. Low entropy means very few. High entropy means almost all of them. Your coffee cools and your cup breaks for the same reason the deck never comes back. There is more room in the direction of mess. The card analogy breaks in one place, and the place it breaks is going to matter later, so notice it now. A deck has a fixed and finite number of arrangements, 52 cards, and a number you could write down if you had an afternoon. The universe is not so tidy. Whether the number of things the universe can do is finite or infinite is an open question, and grown physicists have been fighting about it for 20 years. Now, the second law does something else for you, something you use every waking second without noticing. It gives you a past. You know what happened yesterday because there are records, photographs, receipts, a text message with a timestamp, dirty dishes, the ache in your legs from the walk. Every one of those is a low entropy structure sitting in the present, and every one of them exists because entropy was lower before and higher now. A record cannot be anything else. Memory works the same way, written into the arrangement of cells inside your skull, obeying the same rule as the ash and the sand. Think about what a photograph actually is, not the picture, the object. A sheet of matter holding one very particular arrangement, and that arrangement got there because something else pressed itself into it. A print in wet sand works the same way. So does a scar. So does the layer of ash in a rock that tells a geologist a volcano went off. All of them are the present, holding a shape it was handed, and all of them only work in one direction. There are footprints of the past everywhere you look. There are no footprints of the future. Not one, anywhere, ever, in the entire recorded history of anyone paying attention. That asymmetry is not a rule someone wrote down. It falls out of the fact that entropy behind you is lower than entropy in front of you. So the arrow points one way. Cause before effect. Cause you remember. Effect you live in. The whole shape of a human life is built on that gradient, and Boltzmann was the man who explained why the gradient exists at all. 3 things before we go further. I'm going to say them once each and then leave them alone. First, the proof Boltzmann built has a feature nobody puts in the textbook summary. It runs in both directions. Second, empty space, the truly empty kind, with nothing in it at all, is not at zero temperature. Not quite. Third, when a model of the universe predicts that you are wrong about everything you think you know, physicists usually say the model is broken, not you. Hold on to that sentence. It is going to turn around and look at you. Boltzmann published the theorem in 1872. It is called the H theorem, and it was meant to be the bridge between two worlds. On one side, atoms bouncing off each other, obeying Newton, perfectly reversible, no preferred direction. On the other side, the world you live in, where heat flows one way and eggs do not unscramble. He wanted to show that the second world falls out of the first. He nearly did. 23 years later, in a letter to the journal Nature, he wrote down what he had actually proved, and it is worth being precise about it, because almost everyone gets this wrong. He said it could never be shown from the equations of motion alone that the quantity he called h must always decrease. It could only be deduced from the laws of probability. If the starting state is not specially arranged for some purpose, then the odds favor a decrease. He was careful. He used the word probability. He said the result holds on average. Now put that carefully in your hands and turn it over. Probability does not know which way time runs. The equations underneath do not know either. Newton's laws work perfectly well backwards. Film a collision between two atoms, run the film in reverse, and there is nothing in the footage a physicist could object to.
So when Boltzmann's argument says that a low entropy state is overwhelmingly likely to be followed by a higher entropy state, the same argument, with the same math, says it was overwhelmingly likely to have been preceded by one. Take a single moment, any moment, this one. Suppose all you know is that the entropy right now is low. Not how it got low, just that it is. What does the theorem predict? It predicts that entropy was higher a minute ago, and higher an hour ago, and higher a year ago. It predicts that you are standing at the bottom of a valley and that the ground rises behind you exactly as steeply as it rises ahead. And now, the piece that turns this from a curiosity into something worse. Everything you know about the past is present tense information. The photograph is a pattern of ink that exists now. The memory is a pattern of neurons firing now. The fossil, the tree ring, the light from a distant star, all of it is arriving here in this instant and being read here in this instant. You have never once had direct access to yesterday. You have only ever had access to the present state of things that appear to be about yesterday. So if you condition on the present alone, which is all you actually have, the mathematics says the low point is here, now. And the past with higher entropy than the present is a past with no order in it, no structures, no earth, no childhood. No science channel invented that paradox. It falls straight out of the ordinary reading of an ordinary theorem, and physicists have been arguing about how to escape it for 130 years. To understand how they got here, you have to go back to Vienna and to a man who was losing an argument. Picture the 1890s. Boltzmann is a professor in a city that will shortly produce Freud, Mahler, and half of modern thought. He is short, heavily bearded, terribly nearsighted, and famous among students for lectures so popular that people stood on the staircase to hear them. He is also, in the eyes of a large part of the German-speaking physics world, wrong about something basic. He believes in atoms. That sounds absurd now, but atoms in 1890 were not a fact. They were hypotheses, and a suspicious one. Nobody had seen an atom, nobody could weigh one. Ernst Mach, a philosopher and physicist of enormous influence, thought that science should describe what can be observed and nothing else, and atoms could not be observed, so atoms were metaphysics dressed up in numbers. Wilhelm Ostwald, a brilliant chemist who would go on to win a Nobel Prize, believed energy alone was fundamental and that the atomic picture was a crutch. These were not cranks. These were the most respected voices in the field, and Boltzmann's entire life's work sat on the assumption they rejected. Then came the objections from inside the house. The first one arrived from a colleague and friend, Josef Loschmidt. His point was simple enough that a child could follow it, and deep enough that it is still being worked on. If the underlying collisions are reversible, he said, then for every process where entropy rises, there is an exactly mirrored process where entropy falls. Just reverse every velocity. The reversed motion is legal physics. So how can an irreversible law come out of reversible parts? Boltzmann's answer was the probability answer. The reverse states exist, he said. They are simply so rare that you will never meet one. The second objection was worse, and it came in 1896 from a young mathematician named Ernst Zermelo. He had been reading a paper by Henri Poincaré. Poincaré had proved something startling about any closed system that cannot escape to infinity. Wait long enough and it comes back. Not approximately, arbitrarily close to where it started. Every atom, every velocity, near enough to identical that you could not tell the difference. This is called the recurrence theorem, and it is not a guess, it is a theorem. Zermelo's use of it was surgical. If the system must return to its starting state, then a graph of its entropy over time has to be a repeating curve. Up, then down, then up again, forever. And the second law says entropy only ever goes up. Both cannot be true. Zermelo concluded that the whole atomic project was a dead end. Poincaré himself had already seen where this leads, and he wrote it down 6 years earlier with a kind of amused menace.
The world, he said, tends first toward a state where it remains for a long time without visible change, which matches what we see. But it does not stay that way forever. It stays that way for an enormously long time. What comes after is not final death, but a sort of slumber, from which the world will wake. And to watch heat pass from a cold body into a warm one, he wrote, you do not need the sharp eyes and quick hands of Maxwell's demon. In his words, it will suffice to have a little patience. The exchange that followed was not polite.
Boltzmann and Zermelo went at each other in print, paper after paper, across 2 years and several journals. Boltzmann was convinced the young man had simply missed the point. Zermelo was convinced the older man was hiding a hole in his argument behind the word probability. Read the letters now and you can feel a professor who has already explained this 3 times and is running out of patience with a world that will not follow him. Boltzmann's reply was to reach for a number. He sat down and estimated the weight. How long before the air in 1 cubic centimeter of space, a volume smaller than a sugar cube, returns by chance to a configuration it held before? The answer he got was a number so large that you cannot write it out. Not because the number is big, because the number of digits in the number is big. He was not describing a long time. He was describing a length of time that makes the age of the universe indistinguishable from a single heartbeat, and he thought that settled the matter. In one sense, it did. Nobody is ever going to see a cup unbreak. In another sense, he had just conceded the entire game and did not notice. He had agreed that recurrence happens. He had only argued about the schedule. And there is one more thing both sides of that fight got wrong, and it is the reason we are having this conversation at all. Boltzmann and Zermelo and Mach and Ostwald all assumed the same background. They assumed the universe was eternal and essentially unchanging. No beginning, no end, just a stage that had always been there. Every one of them was wrong about that, and the way in which they were wrong took another 102 years to show up. Jump forward. It is 1998, and 2 rival teams of astronomers are chasing the same number with the same technique and, honestly, a fair amount of hostility toward each other. The technique is exploding stars. A certain kind of supernova detonates at almost exactly the same brightness every time, which means that if you find one and measure how faint it looks, you know how far away it is. Find enough of them at enough distances and you can chart how fast the universe was expanding at different points in its history. Saul Perlmutter had been building his team, the Supernova Cosmology Project, since 1988. Brian Schmidt put together a competing group in 1994, and a young researcher named Adam Rees led the analysis of their data. Both teams were looking for the same thing, and both expected the same result. They expected the expansion to be slowing down. That was not a wild guess, it was the obvious prediction. The universe is full of matter, matter pulls on matter, and gravity is always attractive. The only real question was whether the braking was strong enough to eventually stop the expansion and pull everything back together. The data came back wrong. Not wrong in a small way. Wrong in a direction nobody had ordered. The distant supernovae were fainter than they should be, which meant they were further away than they should be, which meant the expansion had not been slowing, it had been speeding up. Something was pushing space apart, and the further apart it got, the harder the push. Both groups spent months trying to kill their own result. That is what you do when the answer is embarrassing. You look for dust. You look for a calibration error. You look for anything that would let you not have to stand up in front of your colleagues and say that the universe is behaving impossibly. Neither team could make the problem go away, and neither wanted to be second to publish. The papers came out in 1998 and 1999. The journal Science called it the breakthrough of the year. The Nobel Prize followed in 2011. We call the cause dark energy, which is a name and not an explanation. In the simplest version, it is a fixed energy that belongs to empty space itself, and it does not thin out as space grows. More space means more of it, which means the push gets stronger, forever. Now here is what that did to the future. For most of the 20th century, there were 2 respectable endings. Either gravity wins and everything collapses back into a fireball, or expansion wins and everything drifts apart and cools toward nothing. Both endings were finite in a useful sense. A collapsing universe stops, an emptying universe empties out and there is nothing left to do. Acceleration gives you a third ending, and it is not like the other 2. The universe expands forever, faster and faster, until the galaxies have all fled past each other's reach, and space is essentially empty. And then it keeps going. It settles into a shape physicists call de Sitter space, after Willem de Sitter, who worked out the geometry back in Einstein's day. Empty, smooth, expanding at a steady exponential rate. Forever is the important word. Not a long time. Forever. It is worth walking through what that future actually looks like, because the numbers get abstract fast and the picture does not.
Star formation runs out of gas. The last small red stars, the stingy ones that burn for ages, gutter out somewhere around 100 trillion years from now. After that, the sky belongs to corpses. White dwarfs cooling toward black. Neutron stars. Black holes eating whatever wanders close. Galaxies slowly come apart as stray gravitational encounters fling their contents into the dark. Then even the black holes leak away, one photon at a time, over spans of time with 100 zeros in them. And after all of that, the universe is not finished. It is simply empty. Cold, smooth, stretching, with nothing left in it to happen to.
Whatever a descendant of ours might see overhead at that point, it would not include a single star, because by then there would not be one anywhere to see.
That state is where we are heading, and according to the simplest reading of the data, we settle into it and stay. And there is a detail about that empty forever which I mentioned earlier and dropped. Empty de Sitter space has a horizon, a boundary past which light can never reach you because the space in between is being stretched too fast. And the horizon, it turns out, is not nothing. What that horizon does is the whole rest of this story. But it has a prologue, and the prologue was written in 1895 because Boltzmann had already imagined this ending. He put it in a footnote. The letter is short. It ran in Nature in February of that year, 3 pages, mostly a technical defense of his work against critics writing in the same journal. He answers them point by point. And then, in the last few paragraphs, almost as an afterthought, he changes the subject entirely and proposes a picture of the whole cosmos. He does not propose it as his own.
He opens by saying he will close the paper with an idea from his old assistant, Dr. Schutz.
The idea goes like this. Suppose the whole universe really is in thermal equilibrium and has been forever and always will be. Dead, uniform, nothing happening. Fluctuations still occur because fluctuations always occur. A region here or there dips away from equilibrium by chance. The further the dip, the rarer it is. But, and this is the move, the probability of finding some small patch in some particular state goes up as the universe gets bigger. Make the universe large enough and you can make the odds of a patch like ours as good as you like. Boltzmann puts the objection into his own mouth before anyone else can. Somebody will say our world is so far from equilibrium that we cannot even conceive of how unlikely it is. True, he answers, but can you conceive of how small a part of the whole universe this world is?
In a paper the following year, he makes the picture explicit, and it is a genuinely strange thing to read from 1896. He describes a universe that is in equilibrium as a whole, and therefore dead, containing here and there relatively small regions the size of our galaxy, which we call worlds, and which spend brief spans of eons far from equilibrium. He says that for the universe as a whole, the two directions of time are indistinguishable, the way there is no absolute up or down in space. A living being inside one of those regions defines its own past and future by which way entropy runs locally, the way you define down on the surface of the Earth by pointing at the center. Sit with what that means. In 1896, before general relativity, before anyone knew there were other galaxies, before the Big Bang was even a phrase, a physicist in Vienna wrote down a multiverse, an anthropic argument, and a subjective era of time. He treated all three as a throwaway idea from his assistant. The assistant appears in the literature as Dr. Schutz and almost nowhere else. One line, credit for one of the strangest ideas in physics, and then nothing. History does not even reliably record his first name. There is a small human detail about how that letter came back into circulation, and Carroll has told the story. When modern cosmologists started arguing about all this, in the 2000s, most of them had never read the original. Alexander Vilenkin tracked down the reference. Don Page went to a library and copied the pages out of a crumbling leather-bound volume. Andreas Albrecht scanned the copy so everyone else could see it. 3 prominent physicists ran in a small relay race to retrieve 3 paragraphs written before anyone had heard of an X-ray, an electron, or a nucleus. Boltzmann seems pleased with the idea. He does not seem to have noticed the problem inside it. His own logic eats itself, and it took 36 years for anyone to say so out loud. The person who said it was Arthur Eddington in 1931 in a paper with a title that tells you exactly what kind of mood he was in. He called it The End of the World from the Standpoint of Mathematical Physics, and he published it in Nature. Eddington's objection fits in a single sentence, and the sentence is a knife. He wrote that the universe containing mathematical physicists will, at any given date, be in the state of maximum disorganization, which is not inconsistent with the existence of such creatures. Read it again slowly, because it does not look like an attack. It looks like a definition, and it destroys the whole picture.
Follow the logic. Boltzmann says we exist because of a rare fluctuation. Fine, but rarer fluctuations are exponentially rarer. Every extra bit of order you demand costs you, and the cost compounds viciously. So if the only thing the universe needs to produce in order for anyone to be here asking questions is an observer, then the cheapest fluctuation that does the job is the one that will actually happen. Overwhelmingly, not by a small margin, by a margin with 100 zeros in it. So ask what the job actually requires. Does it require 100 billion galaxies? Obviously not. You could have one galaxy and the question still gets asked. Does it require a galaxy? No, one star with one planet would do. Does it require a star? Not really. You need a warm room, a body, and a functioning brain. Does it require the room? Does it require the body? You see where the flaw is. Think about a page of typed text with a single typo in it. One wrong letter on a page is nothing. It happens all the time. You barely notice. Now imagine that instead of one typo, a random process produced an entire correct chapter. Every word spelled right, every sentence grammatical, purely by accident. Those are not two versions of the same event. They are separated by a gulf so wide that the first happens constantly and the second has never happened and never will. Every additional letter you demand multiplies the improbability. Order is expensive, and it is expensive per unit. Where the comparison fails is that a typo is a small deviation from something that already exists. The universe in Boltzmann's picture is not correcting the draft, it is composing from noise, with nothing on the page to start from. That makes the cost worse, not better. So Eddington's razor cuts, and it keeps cutting, and it does not stop at the galaxy, or the solar system, or the room. It stops at the smallest thing that can hold a thought. Nobody in 1931 used the word that came later, but that is the moment the idea was born. For about 30 years it sat there, mostly ignored, a curiosity for people who liked worrying about the arrow of time. Then it got picked up by someone who thought it was too important to leave in the journals. Richard Feynman was lecturing to first-year undergraduates at Caltech in the early 1960s. The lectures became 3 famous red books. Most of the material is what you would expect: forces, waves, electricity. And then there is a chapter on a small mechanical toy, a ratchet and a spring-loaded pole. He uses it to build up the second law from scratch. In the last few pages it turns into a discussion of the origin of the universe. The toy is worth a moment, because it is the cleanest demonstration of the second law anyone has built out of household parts. Imagine a box of gas with a paddle wheel inside it, on an axle. Gas molecules bang into the paddles from every side, so the axle jitters back and forth at random. Now put a toothed wheel on the other end of the axle, with a little spring-loaded catch resting against the teeth. The catch lets the wheel turn one way and blocks it from turning the other. Free energy. Tie a thread to the axle and lift the weight with nothing but the warmth of the air. It does not work, and the reason it does not work is beautiful. The catch is also made of atoms, and it is also being jostled. Every so often it bounces up off a tooth at exactly the wrong moment and the wheel slips backward. Run the numbers and the two effects cancel exactly, as long as both ends of the machine are at the same temperature. The wheel wanders, it gets nowhere. Feynman says that getting nowhere is the deepest principle in all of thermodynamics. Feynman thought 18-year-olds should know this, not graduate students, 18-year-olds. He lays out the fluctuation idea plainly, and then he does something better than arguing about it. He gives you a test. If the order around you is the result of a fluctuation, he says, then you should reason like this. A big fluctuation is far less likely than a small one. So the most likely fluctuation that could produce what you have already seen is the smallest one that does the job, and no larger. Which means that when you look somewhere you have not looked before, you should find it mixed up, disordered, nothing like the piece you were standing in. That is a real prediction, and you can check it. The check runs every clear night on every mountaintop with a telescope on it. Astronomers point at stars nobody has examined before. They do it constantly. It is most of what observational astronomy is. And the new stars are not chaos. They burn hydrogen, they sit on the same diagrams, they follow the same laws, they have planets, they are made of the same elements in roughly the same proportions. Every new patch of sky comes back looking like the old patch of sky. Feynman's conclusion was blunt. The universe is not a fluctuation, and the order is a memory of conditions when things started. He immediately adds that he does not claim to understand the logic of it. For some reason, he says, the universe once had extremely low entropy for its energy content, and it has been climbing ever since. That climb is where irreversibility comes from. It is why things grow and decay. It is why you remember the past and not the future. And Feynman puts it beautifully. You remember the things that are closer to the moment when order was higher, and you cannot remember the things on the side where disorder is higher, which is the side we have agreed to call the future. So there it is. The test was run. The fluctuation picture failed. Boltzmann's cosmology went into the file marked interesting and wrong, and physics moved on for another 40 years. The only trouble is that Feynman's argument has a hidden assumption in it, exactly the way Boltzmann's did. It works if the universe gets to run out of time. It works if the show ends. In 1998, two teams of astronomers found out that the show does not end. Boltzmann did not live to see any of it. He never learned that the universe had a beginning. He never heard anyone use the word galaxy the way we use it now, as one island among 100 billion. And he never found out that he had won the argument of his life. In 1905, a patent clerk in Bern published a short paper about the trembling of tiny particles suspended in water. Albert Einstein showed that the trembling was atoms, and that if you measured it carefully enough, you could count them. Within a few years, Jean Perrin had done exactly that in a laboratory in Paris. The counting worked, the numbers matched. Atoms were not philosophy anymore. Boltzmann does not seem to have believed it had happened. By 1906, his health had collapsed. Asthma, headaches that would not leave, eyesight so poor that he could no longer read papers himself and needed them read aloud to him. People close to him recorded that he lived with a specific fear, which was standing in front of a lecture hall and losing his mind and his memory in front of the students. That spring, a physician examined him, diagnosed what was then called neurasthenia, and told him to stop scientific work completely. 4 months later, he was on holiday with his wife and his daughter at the Bay of Duino, near Trieste, on the Adriatic coast. On the 5th of September, while the two of them were swimming, Ludwig Boltzmann took his own life. He left nothing written to explain it. The tempting version of this story is that the critics killed him. It has been the popular version for 120 years, and it gets retold with the detail that even his opponents grieved, that Ostwald himself, the man who had fought him hardest, spoke of him afterwards with real warmth. The historians who have looked hardest at the record are not so sure. They point out that there had been an earlier attempt years before, in Leipzig, well before the arguments reached their worst. They point at the asthma, the eyes, the diagnosis, the sheer physical exhaustion of a man who could not work and had built an identity out of nothing but work. Whether the science had anything to do with it is not a settled question, and I am not going to pretend it is. Nobody knows. That is the whole answer. He is buried in the Zentralfriedhof in Vienna. Above the grave there is a bust, and carved above the bust there is an equation. It is his own. It says that entropy is the logarithm of the number of arrangements a thing could be in. The formula that counts possibilities, cut into stone over the one place a man permanently is. That formula went quiet for most of the next century. Nobody needed the fluctuation idea. Feynman had tested it and thrown it out. The universe had a beginning now, and beginnings make the whole problem go away. Then the sky turned out to be accelerating, and the fluctuation idea came back through a door nobody had thought to lock. The paper appeared in 2002 with 3 names on it: Lisa Dyson, Matthew Kleban, and Leonard Susskind, one of the founders of string theory, a man who has spent his career on problems that would give most people vertigo and who does not startle easily. They gave it a title more honest than most papers get: Disturbing Implications of a Cosmological Constant. Their argument starts with a piece of physics from 1977 that most people outside the field have never heard of. Gary Gibbons and Stephen Hawking had just worked out what happens at the horizon of a black hole. Then they asked whether the same reasoning applies to the other kind of horizon, the cosmological one, the boundary in every direction past which the expansion is too fast for light to ever cross back to you. It does apply. A cosmological horizon behaves like a warm surface. It radiates. Now, the temperature is absurd. For our universe, with the amount of dark energy we measure, it comes out to a fraction of a degree above absolute zero, with about 30 zeros after the decimal point. Set that against the leftover glow of the Big Bang, which fills all of space at a few degrees above absolute zero and is already colder than anything that happens naturally on Earth. The horizon is colder than that by a factor with 30 zeros in it. You will never measure it. Nothing will ever measure it, but it is not zero. Take that one fact and hold it against everything from the first half of this story, and the floor goes. Classically, an accelerating universe empties out and dies at zero temperature, and nothing further happens, ever. Quantum mechanically, it empties out and settles at a fixed, tiny, permanent temperature and stays there for the rest of time, which means it is not a corpse. It is a bath. A sealed room, faintly warm, with a thermostat that never switches off, and no door. which is Boltzmann's picture, exactly his picture. An eternal system in thermal equilibrium with statistical fluctuations in it. The thing Eddington killed and Feynman buried returned after a century, except this time nobody proposed it. It came out of the equations as a consequence of a measurement. Think about a lottery machine in an empty room, tumbling numbered balls, and nobody ever comes to switch it off. The odds of any particular combination are terrible. It does not matter. The machine is not going to stop. Run it for long enough and every combination comes up, and then comes up again, and the machine keeps going. The improbability of a single draw stops meaning anything the moment the number of draws stops being finite. That is the whole mechanism, and it is why this problem cannot be waved away with a big number. Big numbers lose to forever. They always lose to forever.
The comparison fails in one respect, and the failure is interesting.
A lottery machine is fed electricity by somebody. The horizon is not being fed by anyone. It radiates because of the geometry of an expanding space, which is to say, it radiates for free, which is to say, there is nothing to unplug. Dyson, Kleban and Susskind pushed further into an idea called horizon complementarity, where everything inside your horizon is described by a finite amount of information written on the horizon itself. Finite is the operative word. A system with a finite number of possible states is exactly the kind of system Poincaré's recurrence theorem was written for. It cannot settle down forever. It has to keep trying things. Their conclusion, in the flat language of the abstract, is that these assumptions lead to very deep paradoxes, and that something we currently believe is going to have to be given up. What should bother you most about this is not the exotic part.
It is how ordinary the ingredients are. You do not need string theory to get here. You do not need eternal inflation or parallel universes or any speculative machinery at all. You need the standard model of cosmology, the one built by fitting thousands of measurements from dozens of instruments, the model that has been right about the microwave background and the abundance of helium and the growth of galaxies. Take that model, run it forward with a constant dark energy, and it predicts nonsense. The field noticed. Papers started appearing quickly, and the speed itself became part of the story. One of the more consequential responses was written in 2 days flat, by 2 men working against the clock because they were afraid somebody else would get there first. The name arrived in 2004. Andreas Albrecht at Davis and Lorenzo Sorbo working on a paper with a title that reads like a question from an accountant. Can the universe afford inflation? Buried inside it is the phrase that escaped the journals and got loose in the world. Boltzmann Brain.
Their logic is the logic Eddington started and nobody had finished. If the criterion for anything to matter is that there be an observer, and if fluctuations are penalized exponentially for every scrap of order they contain, then the observers that actually get produced are the cheapest ones. Not people, not bodies. The minimum arrangement of matter that qualifies as a mind, sitting in equilibrium with nothing around it. Albrecht has made the point, with some amusement, that credit here is complicated. He suggested that in order to preserve the alliteration properly, the things should really be called Schutz's Schmarz, after the assistant who actually had the idea. It did not catch on. Nothing named after Dr. Schutz ever does.
Cosmologists needed a second term too, for the kind of observer you and I believe ourselves to be.
And the terminology they settled on is worth hearing because of how blunt it is. We are called ordinary observers.
In papers, it gets shortened to 2 letters.
The others are called freak observers. That is the technical phrase used by Alexander Vilenkin in a paper title. Freak observers versus ordinary observers. And the entire question is which sort you are. By January of 2008, the argument had moved far enough out of the journals that the New York Times ran a long piece on it, under a headline that captures how the rest of physics felt about the whole business. Big brain theory, it asked. Have cosmologists lost theirs? And this is the moment to be extremely clear, because the honesty is what makes this frightening rather than silly. No physicist believes you are a Boltzmann brain. Not one. Sean Carroll, who has written more carefully about this than almost anyone, keeps having to repeat the point, because people skip past it in their excitement. The Boltzmann brain was never a discovery.
It works as a demolition tool, the thing you throw at a cosmological model to find out whether the model comes down.
The trouble is that the current model does not fall down cleanly. It stands there, absorbing the blow, and refuses to say whether it is broken. So the next question is a mechanical one, and it is where this stops being philosophy and starts being genuinely unpleasant to picture. What would actually have to happen, physically, for a mind to assemble itself out of nothing? Go there. Not to the empty sky at the end of time in the abstract, but into it. There is no matter left. Understand how thoroughly that is meant. The temperature of that space is so low that it cannot support even the lightest particles that have mass. Electrons are far too heavy for it. What remains, drifting through an endlessly stretching volume, is massless. Photons, gravitons, if gravitons are real, and most physicists think they are. That is the entire inventory of the universe.
Light too faint to see by,
and ripples in space too small to name. Almost nothing interacts because there is almost nothing to interact with, and space keeps opening up between the things that are left. But occasionally, two photons at the high end of that faint distribution run into each other with enough energy between them to make something. A pair of particles condenses out of the collision, an electron and its antimatter twin. Given the odds, they almost always find each other again immediately and annihilate back into light, and the universe returns to exactly what it was. Almost always. Not always. Once in a while, the pair flies apart hard enough to escape each other. Now there is a particle of matter in a universe that has none. It drifts, space stretches around it. Once in a much longer while, that happens twice in the same neighborhood. Then 3 times.
Then, across spans of time that make the edge of the cosmos look like nothing, it happens enough times and close enough together to leave a small cloud of ordinary matter sitting in one place, with nothing else around it for unimaginable distances. And then the arrangement problem starts. And the arrangement problem is the hard part. The particles are there, they now have to fall into precisely the pattern of a functioning brain, with its membranes and its ion gradients and its 100 trillion connections weighted in exactly the configuration that encodes a specific human life. Here is the detail that I found genuinely difficult to stop thinking about, and it is not speculation, it follows from the time symmetry we have been circling this whole time. It is tempting to picture the thing appearing in a flash, a sudden pop, a brain materializing out of the dark, blinking on like a light. That picture is wrong, and it is wrong for a reason you can derive. Take the time symmetry of the underlying laws at face value, which is what the people working on this do, and the process that builds a Boltzmann brain is the reverse of the process that destroys one, not similar to it. The reverse in the strict mathematical sense, because nothing in the physics distinguishes the two directions. So, ask how it ends. It ends slowly. It sits in a vacuum with no oxygen and no blood pressure. It stops working, it cools, it freezes, and then, over an enormous stretch of time, its molecules wander off one by one until nothing is left. Which means it began the same way, played backwards. Molecules wandering in from the emptiness, one by one, over the same enormous stretch of time. Assembling, slowly, in the dark, in the cold, with no cause anywhere directing it and no plan being followed. Each particle arriving at the only position it could have arrived at for the pattern to close. Carroll goes one step further than that, carefully and with hedges, because the link between physical time and experienced time is not something anyone claims to have nailed down.
If the finished brain is conscious for its brief life, he notes, it is natural to think it was conscious during the assembly as well, running backwards, experiencing an arrow of time pointing the other way. There is no established science on what that would be like. There is not even a good framework for asking. So I will leave it exactly where the physics leaves it, which is as an open door with nothing visible past it. What we can say is what happens at the moment the pattern closes. For an instant, there is a mind. It has no body, no lungs, no heart, no blood moving anywhere. It is not in a room, it is not on a planet. There is no planet and has not been one for longer than there are words for. What it has is a complete biography. It remembers a childhood. It remembers what it ate this morning. It remembers a face it loved, an argument it lost, the specific quality of light in a room it grew up in. All of that is present in full detail in the arrangement of the matter, because that is what a memory is, a physical pattern. And a physical pattern can be arrived at from any direction. None of it happened. It thinks a few thoughts. That is the technical criterion the papers actually use, from Davenport and Ollum at Tufts, who define the objects as brains that last at least long enough to think a few thoughts. Then the pressure differential and the temperature and the absence of oxygen do what they do, and it ends, and the pattern comes apart, and the universe carries on exactly as before. Now here is why this is not a horror story about somebody else. Ben Freivogel, who spent years on this problem, points out that the fluctuation picture makes a prediction you can check with your own eyes. If you are a typical observer in that kind of universe, then everything beyond your immediate perception is still in equilibrium, which means when you look up, you should see nothing. Not a dark sky with a few stars, a blank one. No moon, no planets, no band of the Milky Way, no light at all from anywhere, because there is no anywhere. You know what your sky looks like. You have seen it, so go and look tonight. Genuinely, step outside or open a window and look up, and if there are stars, then you have just personally run an observational test on a cosmological model using equipment you were born with. Freivogel puts the day in the coldest possible way in his own writing. If your delusion holds together long enough for you to finish reading his article, he says, you may safely discard the theory. Same offer. If you are still here at the end of this video and the sky is still full, then the simplest version of the fluctuation picture is dead. Keep that there in your pocket. There is a version of this argument that survives the test, and it was built specifically to survive it. First, the numbers, because they are the only way to feel the size of what we are talking about, and because they are the reason 100 physicists could not simply laugh this off. How improbable is a brain? You measure it by asking how far the entropy has to fall to make one. Start with the raw materials. A human brain weighs about as much as a bag of sugar, and it holds roughly a billion protons and neutrons. That is more particles in the thing between your ears than there are stars in the entire observable universe, by a factor of thousands. Every one of them has to come out of the thermal bath and land in exactly the right place. And the published estimates of the entropy cost run far higher still. The count is not of particles, it is of all the arrangements those particles could have taken instead. The probability sits in an exponent with a minus sign in front of it. The odds that come out are not 1 in a billion or 1 in a trillion. They are 1 in a number that would take you the rest of your life to read aloud. That is why nobody worried about this for a century. On any human timescale, on any planetary timescale, across the entire history of the universe so far, it does not happen. Not almost never. Never. Against that stands one other number, and it is the one that decides the argument. The horizon around us encloses a certain amount of information, and there is a standard way to calculate how much. The answer, in the units physicists use, is a number with more than 120 zeros after it. Zeros are hard to feel, so hold the shape of it instead. Count every particle in every galaxy your telescopes can reach. Now multiply that total by itself, and multiply the result by itself again, and you are still climbing. Each of those 120 zeros multiplies everything in front of it by 10, and they keep coming long after your ability to picture anything has quit. That number sets the clock. The time it takes a system that size to come back around near where it started is that already unspeakable quantity raised into an exponent of its own. And this is where it stops being arithmetic and turns into something else. The result is so large that the units stop mattering. Measure it in seconds and you get an answer. Measure it in the smallest interval physics recognizes, or in complete ages of the universe, and you get a number that is, for every practical purpose, the same one. Changing the unit shifts it by a rounding error at the very top of the exponent. There is no clever way to hold this number. It does not shrink when you handle it carefully, which is what the empty universe has to work with, and it is why the arithmetic was never going to save anybody. The rarity is real. The rarity is also the only defense on offer, and it is being asked to hold out for the rest of time. Which brings us to the objection you have been forming since the last section, and I want to give it to you properly, because it is the right objection, and it has a documented answer. You are not a disembodied brain. You are obviously not. You have hands, you can feel the chair. There is a room around you, with a specific arrangement of objects in it, and outside the window there is a street, and the street is where it was yesterday. Carroll wrote out this exact exchange in a paper called Why Boltzmann Brains Are Bad. He sets it up as a conversation between two scientists, one worried and one not, and he lets it run until it stops being comfortable. The relaxed one says what you just said. I do not look very brain-like. I have arms and legs. The world around me is dramatically far from equilibrium, and the fluctuation would not bother producing all of this. The worried one agrees, and then moves the goalposts to where they actually belong. Fine, he says. Suppose you are not the minimum possible fluctuation. In a randomly fluctuating universe, you are still overwhelmingly likely to be the minimum fluctuation consistent with whatever you happen to be observing. Given that you have arms and a chair and an office, the cheapest way to produce all of that is for exactly that much to fluctuate into existence and nothing more. These are not Boltzmann brains anymore. The papers call them Boltzmann observers. Notice what that quietly concedes. Your body does not protect you, and neither does your room. Whatever you hold up as evidence simply gets folded into the description of what fluctuated. The fluctuation grows a little, absorbs the evidence, and carries on being the cheap option. Because look at what the alternative has to buy. A genuine history means the universe set in a state of staggeringly low entropy 14 billion years ago. Then it made hydrogen, then stars, then heavy elements cooked inside those stars, then a second generation of stars, then a planet, then chemistry, then 4 billion years of biology, then a civilization, then your parents. Every stage of that is an entropy debt, and the debts stack. Or the last few seconds of it could assemble directly, memory included, and skip the bill. The version of you sitting there recalling the walk into that room does not cost more than the version that walked in. It costs unimaginably less. And in a universe that runs forever, the discount always wins. So you reach for the obvious test, and I want to walk through why it does not close the door. The test is repetition. If my surroundings are a fluke, then they should not persist. So I look again. I check whether the world is still there. I go outside and the street is still the street. Or, if you want the properly astronomical version, I point a radio telescope at the sky and pick up the microwave background, the leftover heat of the Big Bang, the strongest single piece of evidence that there was a low entropy beginning. I wait, I measure again, it is still there. That is Feynman's test, and it is a good test, and against the crude version of the fluctuation picture, it works. The answer that undoes it is uncomfortable in a very specific way. Among all the observers in an eternally fluctuating universe who have data exactly like yours, including the memory of having checked, including the second measurement, including the relief of finding the sky unchanged, the overwhelming majority are fluctuations too. They are simply slightly larger ones. The check is now part of the pattern that had to be produced, and producing it costs a little more, and a little more is nothing against forever. You can condition on anything you like, any fact about your situation, any measurement, any amount of evidence. It all gets absorbed. The set of fluctuations matching your description shrinks, and it stays infinitely larger than the set of real histories. Underneath this sits a property of physical law so basic that it is easy to miss. The laws are memoryless. Physicists borrow a term from probability and call them Markovian. What that means is that the present state of a system is enough to determine what happens next. The past is not an ingredient. It does not need to be consulted. Nothing in the equations reaches backwards to check whether the history was real, which has a consequence for every piece of evidence you have ever trusted. A photograph of a birthday party does not require that there was a birthday party. It requires that there is, right now, a piece of paper with a particular distribution of ink on it. In the world you believe you live in, the party is by far the best explanation for the ink. In the world the equations describe when you let them run forever, the ink is just ink, and it did not come from anywhere, which is roughly where the field found itself around 2006, and where it started to come apart from the inside. Don Page published a paper that year, taking the problem seriously enough to draw a consequence from it. We will get to what he proposed, because it is one of the strangest suggestions in modern cosmology. What matters first is what his paper did to two other physicists. Raphael Boussot was at Berkeley. Ben Freivogel had been Susskind's student and was working with him. They read Page's paper and had the same thought at the same moment. And the thought was an inversion. Everyone had been treating Boltzmann brains as a disease. What if they were an instrument? Here was the problem they had been stuck on. When you try to calculate probabilities in a universe that expands forever, everything you want to count is infinite. Infinitely many observers seeing one thing, infinitely many seeing another. To get a ratio out of two infinities, you have to cut them off somehow. Cutting them off means deciding which events happened at the same time, across regions of space that are flying apart faster than light can cross between them. There is no unique way to do that. Observers that far apart cannot synchronize a clock even in principle. Nothing in the physics tells you which slicing is correct, and different slicings give different answers about what is likely. Cosmologists call this the measure problem, and it has resisted everything thrown at it. What Boussot and Freivogel realized is that Boltzmann brains give you a filter. Any recipe for slicing time that predicts most observers are freaks must be wrong, because we are not freaks. Throw that recipe away. Keep going until only a few survive. They wrote the paper in 2 days. Freivogel has said openly why. They were excited, and they were frightened that somebody else would have the same idea before they could publish. It worked for a while. Over several years, a small group of people used this test to kill proposal after proposal, and something close to a consensus formed around one surviving way of counting. The infinities looked tame. Then, Alan Guth, one of the inventors of inflation, and Vitaly Vanchurin proposed a thought experiment that broke it, and the thought experiment is odd even by the standards of theoretical physics. You flip a coin, you do not look at it. You are placed in a cryogenic freezer. If the coin came up heads, they wake you in 1 year. If it came up tails, they leave instructions for their descendants to wake you in 50 billion years. You wake up. You have no information other than the fact that you are awake. Someone offers you a bet on how long you slept. Common sense says the odds are even. The coin was fair. Nothing about waking up tells you anything. The measure says bet on the short sleep, confidently. Because the volume of space is growing exponentially and never stops, so far more of these experiments were started recently than were started 50 billion years ago. And among everyone waking up today, the short sleepers massively outnumber the long ones. Freivogel and his colleagues, working with Stefan Leichenauer and Vladimir Rosenhaus, traced why the calculation behaves this way, and the reason is worse than the result. The long sleep is dangerous. Not because of the freezer, because in the recipe they were using, an observer who waits too long can run into the end of time. The mathematics had quietly built a catastrophe into the future, and everything downstream of it, including the sleeper bet, was just that catastrophe showing through. They put a number on it. Given the parameters that describe our actual universe, that method assigns something like even odds to hitting the end of time within the next 5 billion years. I want to be exact about what that does and does not mean, because this is precisely the place where a channel like this could lie to you and get away with it. Nobody thinks time is going to stop. Freifogel says so in plain language. The end of time is not a prediction about the world. It is an artifact of the counting procedure, a catastrophe that got injected by accident when physicists tried to tame the infinities. Its appearance signals that something large is missing from our understanding of physics over long distances and long times. That is the honest reading, and it offers less comfort than it looks like it does. Notice where the danger actually sits. The catastrophe is not in the universe. It is in the only method we have for making predictions about the universe. And the method was invented to save us from Boltzmann brains, which leaves the field with a short list of ways out, and Don Page owns the first of them. He looked at the same problem everyone else was looking at, ran the logic in reverse, and arrived at a conclusion he was willing to put in a title as a question. He asked whether our universe is likely to be destroyed within the next 20 billion years. He was not being rhetorical. He meant the question, he meant the deadline, and he had done the arithmetic that produced it. His reasoning runs backwards from where everyone else was standing, and once you see the shape of it, you cannot unsee it. Start by assuming the thing you want to be true. Assume we are ordinary observers with a real history. For that assumption to hold, ordinary observers have to outnumber the freaks. Now ask what controls the freak population. It is time and volume, and nothing else. Every additional second that an empty accelerating universe exists, it manufactures a few more of them somewhere in its endless growing space. The count only ever goes up. Which means the only way for our side to win is for the counting to stop. Something has to end the universe before the freaks outnumber us. Not slow it down, end it. And Page did the arithmetic on how much time we can afford, and got an answer that sits uncomfortably close to the age of the universe we are already standing in. Our vacuum, he argued, has to be unstable, and it has to decay on a timescale of tens of billions of years, or the whole picture falls apart. He is not describing a fire, or an impact, or a collapse. He is describing something else, and the physics of it has been understood since the late 70s. The idea is that what we call empty space might not be the lowest possible state. It could be a dip in the landscape, rather than the bottom of it. Comfortable, stable to look at, but with a deeper valley somewhere below. If any patch of space anywhere ever tunnels down into that deeper valley, the new state is lower energy, so it expands. A bubble forms, its wall accelerates outward, and it approaches the speed of light. Inside the bubble, the constants of nature have different values. Atoms do not hold together. Chemistry does not exist. Sidney Coleman and Frank DeLucia wrote the founding paper on this in 1980, and their description of it has never been improved on. They called vacuum decay the ultimate ecological catastrophe. They also pointed out the one small mercy in it, which is not much of a mercy. The wall arrives at nearly the speed of light, which means it arrives at the same moment as the light that would have warned you. There is no sky turning strange. There is no siren. Whatever is happening to you stops happening, and there is no interval in which you notice. For a long time, this was a beautiful piece of theory with nothing to attach it to. That changed in 2012, when the Higgs boson turned up at CERN and physicists could finally measure the last number they needed. When you put the measured mass of the Higgs together with the measured mass of the top quark, the heaviest particle we know of, and run the calculation forward, our vacuum does not land in the stable region. It lands in the metastable one, a dip, not the floor. The caveats on that are large, and leaving them out would be lying to you. The result sits almost exactly on the boundary. The uncertainty in the top quark mass alone is wide enough to cross from one side of that line to the other, so the honest statement is that we do not yet know which region we are in. The calculation also assumes no unknown physics exists between the energies we can reach and the smallest scales that mean anything, which is an enormous assumption. And the lifetimes people calculate are so long that the different published estimates disagree with each other by more zeros than anybody bothers to count. Nobody has consensus here. What we have is a measurement that came out unnervingly close to a line, and a line that means something. The one thing that has changed recently is that the mechanism stopped being hypothetical. In 2024, a team working in Trento built a gas of sodium atoms chilled to near absolute zero, tuned into a state where it had two possible phases, one of them false and one of them true. Then they watched. Bubbles of the true phase appeared inside the false one, out of nothing, exactly as the theory says they should, and grew. The result went into Nature Physics. The following year, a group ran the same physics on a quantum annealing machine with thousands of qubits and got the same behavior again. None of that is our vacuum, and no one is claiming otherwise. What they built was a laboratory analog. What it demonstrates is that the process is real. Bubbles of a true or nothing do nucleate inside a false one. The equations were not making it up. So Page's escape route is available. It works. It genuinely dissolves the problem, because a universe with a deadline cannot accumulate an infinite population of anything. The price is the deadline. A physicist looking at that trade might reasonably ask whether there is a cheaper way out. And in 2014, 3 of them argued that we had all made a mistake much earlier in the chain, in the very first step, where we said the word fluctuation. Kimberly Boddy, Sean Carroll, and Jason Pollack put out a pair of papers with titles that sound almost rude in their directness. De Sitter space without dynamical quantum fluctuations. And then, in case anyone missed the point, why Boltzmann brains don't fluctuate into existence from the de Sitter vacuum. Their argument turns on a distinction that physicists use loosely in conversation and then get burned by. When people say the quantum vacuum is seething with fluctuations, they are usually picturing something happening, particles flashing in and out, activity, weather in the emptiness. That picture, they argue, is a misreading of what the mathematics says. A quantum vacuum fluctuation is a statement about the spread of results you would get if you measured something. It is not an event occurring in time. Compare it to being told the average height of people in a country. That number has a spread around it, and the spread is real information. But nobody is growing, nobody is shrinking. The statistic is not an activity. Reading it out loud does not make anything happen in anybody's legs. The vacuum of de Sitter space in this reading is a stationary state. Stationary is a technical word, and it means precisely what it sounds like. The state does not change with time. It has no dynamics. Nothing in it evolves, because there is nothing left to evolve into. For something to actually happen, you need an interaction. You need something outside the system to measure it, or a piece of the system to become entangled with the rest in a way that picks out a particular outcome. In a truly empty, truly settled de Sitter space, there is nothing to play that role. There is no apparatus, there is no environment, there is only the state, sitting there, being described by numbers that never change. If that is right, then Boltzmann brains never form, not rarely, never, across infinite time, because forming is a thing that happens, and nothing happens. The problem dissolves without a deadline, without a doomed vacuum, without any price at all, which is why a lot of people wanted it to be true. It is not settled. There is a serious objection, and it comes from within the same tradition of quantum mechanics rather than from outside it. The framework, called decoherent histories, treats a set of possible histories as real if those histories do not interfere with each other. By that criterion, you do not need an outside observer for something to count as having happened. If you take that criterion seriously, the fluctuations come back. Worse, they come back in a way that does not need dark energy at all. Some analyses find that ordinary flat, empty space, with no cosmological constant whatsoever, will still eventually produce these things given long enough. Carroll himself has written that this is the hardest version of the objection, and that the resolution depends on what you think a quantum state actually is, which is a question that has been open since the 1920s. Theory, in other words, has argued itself into a corner it cannot climb out of on its own, which leaves the possibility that the universe might simply hand us the answer. And in the last 2 years, it has started to look like it might. Everything we have been discussing depends on one assumption that has been quietly load-bearing since the acceleration was discovered. The assumption is that dark energy is constant, fixed, a property of space itself that never changes and never runs out, which is what gives you an eternal de Sitter future and therefore infinite time, and therefore the entire problem. There is an instrument in Arizona on a telescope on Kitt Peak called DESI. It has 5,000 robotic fiber positioners on its focal plane. Each one swings to a target and swallows the light of a single galaxy. The whole array reconfigures itself in about 2 minutes and does it again, night after night, for years. What it is building is a 3-dimensional map of where the galaxies are, and, because light takes time, when they were. In March of 2025, DESI released its second major dataset, and it did not say what anybody expected. When the map was combined with the microwave background and with supernova measurements, the fit preferred the dark energy that changes over time, stronger in the past, weakening now. The preference came in at a little over 4 standard deviations in the strongest combination, which is past the level physicists call evidence and short of the level they call discovery. By April of 2026, the 5-year survey was finished, with more than 47 million galaxies and quasars measured, and the instrument has kept going. Now the balance, because this is exactly the kind of result that gets oversold by everyone in my line of work. It is contested, genuinely, technically contested by working cosmologists. The strength of the signal depends on which supernova compilation you use, and the compilations do not agree with each other.
Some analyses find tension between the datasets themselves, rather than a clean physical signal. Under certain treatments of the long-standing disagreement about the expansion rate, the preference for evolving dark energy drops below the level anyone would bother reporting. This is not a discovery, it is a strong hint held by careful people who are arguing about it in public. But there is a reason theories set up when it arrived, and the reason has been sitting in string theory for years. There is a body of work called the Swampland program, which tries to sort the universes that could exist inside a consistent theory of quantum gravity from those that merely look consistent on paper. One of its central conjectures is that stable de Sitter space cannot be built at all. Not that it is hard, that the mathematics does not permit it. If that conjecture holds, then a genuinely constant dark energy is impossible, and what we are measuring has to be something that evolves and eventually fades. A review published in the summer of 2026 laid out how directly the DESI hints line up with that expectation. Two completely separate lines of work, one from telescopes and one from pure theory, both pointing at the same conclusion. The eternity might not be there. And if the eternity is not there, the Boltzmann brain problem evaporates on its own. No infinite time, no infinite trials, no accumulating population of freaks. The whole structure needs forever to stand up, and forever might simply be a mistake we made in 1998. Which is a strange thing to be relieved about when you look straight at it. The measurement that would rescue you from the possibility of being a fluctuation is a measurement that the universe has an expiry date on its current arrangement. The good news is that nothing lasts. That is the price of the reprieve, and it is not negotiable. There is one more way out, and it is the strangest of them, because it does not touch the physics at all. It attacks the argument. Start with Carroll, who noticed something about the logical structure of any theory that predicts most observers are fluctuations. Suppose the theory is true, then you are almost certainly a fluctuation. Then your memories are junk, your training in physics never happened, the papers you read were never written, and the reasoning you used to arrive at the theory came from a pattern of neurons that assembled at random, which means you have no grounds for believing the theory. He calls this cognitive instability, a theory that cannot be believed without undermining the basis for believing it. His conclusion is unusually strong for a working physicist. He argues that such models should be discarded not because we have evidence against them, but before we go looking for evidence at all, because they do not permit the act of gathering evidence in the first place. That was the sentence I asked you to hold on to, back at the beginning, when I said that if a model predicts that you are wrong about everything, physicists usually say the model is broken and not you. Carlo Rovelli and David Wolpert published a paper in 2024 that takes that move and turns it around to face the other way. Their point is about where the whole argument gets its authority. Every step of it uses the laws of physics, thermodynamics, quantum field theory, the temperature of a horizon. And where did we get those laws? From experiments, from measurements written in notebooks, from records of things that happened before now. So the argument runs on the assumption that the past is real, and then concludes that the past is probably not real. It soars through the branch it is sitting on. Any conclusion you draw from it undermines the evidence you used to draw it, so it never actually gets off the ground. They make the failure concrete with a scenario from the paper, and it is a better argument than it first appears. Imagine a security camera in a shop. In the first version, the footage shows Bob taking money from the register. Anyone watching would conclude Bob is a thief, and they would be reasoning correctly from what they can see. In the second version, the camera was pointed slightly differently, and the footage shows a robber holding a weapon on Bob, just outside the frame of the first recording. Same event, same evidence gathering, completely reversed conclusion. Nothing was wrong with the first inference. The inference was sound. The data was simply partial, and partial data produces confident answers that are wrong, and it produces them with exactly the same feeling of certainty as correct ones. Their claim is that the fluctuation argument is the first recording. It reasons flawlessly from a frame that does not include its own justification. Rovelli reaches, in that paper, for something much older than any of this. The dream of the philosopher Zhuangzi, who dreamt he was a butterfly, and woke and could not settle whether he was a man who had dreamt of being a butterfly, or a butterfly now dreaming of being a man. 23 centuries later, with a telescope in Arizona and a particle accelerator buried under the border between France and Switzerland, we have arrived at a formalized version of the same difficulty, and we are no better at closing it. Their conclusion is not a refutation, and they are careful about that. The hypothesis does not get disproved, it gets relocated.
They say it belongs to a grey ocean of ideas that cannot be ruled out and cannot be taken seriously either, the same water in which you will find the possibility that elves exist and are extremely good at hiding. That is where the argument stood at the end of 2024, and you could exhale there if you wanted to. Most people did. The same group kept working.
On the 3rd of December 2025, David Wolpert, Carlo Rovelli, and Klaus Scharnhorst published a paper in the journal Entropy that does something the previous one did not. It stops arguing about interpretation and writes the problem out as mathematics. What they formalize is the thing this whole story has been circling since the first minute, the claim that entropy grows. They express it as a process with the memoryless property we met earlier, and then they ask a question that sounds like housekeeping and turns out to be the flaw giving way. To predict anything at all from that process, you need a starting condition. You need one moment in time where the value of the entropy is taken as known and fixed. Everything else is calculated outward from there. Physics does not tell you which moment to pick. That is the whole finding. The equations run in both directions, as they always have, and they are perfectly happy to be anchored anywhere.
The choice of where to drive the nail is put in by hand, by us, before the calculation starts. Now look at what everyone in this story has actually been doing. The Boltzmann Brain hypothesis drives the nail into the present. It says, take the entropy as known right now, this second, and calculate outward in both directions. Do that and the past is high entropy noise and your memories are a coincidence. The standard picture drives the nail into the beginning. It has a name, the past hypothesis, and it says, take the entropy as known at the Big Bang and calculate forward. Do that and you get the world you believe you live in, with a real history and reliable records. To make the symmetry impossible to look away from, the authors introduce a third option purely to hold it up next to the other two. They call it the 1000 of the common era hypothesis. Drive the nail into the year 1000. Assume entropy was low then and nothing about what came before it.
The mathematics is fine with this. It handles it exactly as competently as it handles the other two.
It yields a universe in which the medieval world is real and everything earlier is fog. The three of them are the same construction, same equations, same machinery, same status. They differ in one respect only, which is the instant you have decided to trust. The authors state the consequence in the flattest possible language, and the flatness is what makes it land. In this respect, they write, the Boltzmann Brain hypothesis and the second law of thermodynamics are equally legitimate, or equally illegitimate. Read that as carefully as they wrote it, because it is not the claim that you are a Boltzmann brain. They are not saying that. Nobody is saying that. They are saying that the argument you would use to prove you are not one, and the argument someone would use to prove you are, both rest on a choice that physics declines to make for you.
The confidence you feel about yesterday is not being supplied by the equations. It is being supplied by you before the equations start, and then the equations dutifully return it to you looking like a result. Your belief in the past is not a conclusion of physics, it is an input. That is the quietest sentence in this entire story, and it is the one that should keep you up. So what does a science do with a hole like that in the floor? It builds around it, and the building is genuinely impressive. Boltzmann brains have become a tool, and one of the sharpest instruments theorists have for a domain where experiments are impossible. If your cosmological model predicts that most observers in it are freaks, the model is disqualified. You do not need to observe anything new. You do not need funding or a satellite. You just need the model to have said something absurd about the people doing the modeling. That test has done real work.
Whole families of proposals for how to count probabilities in an infinite universe have been eliminated with it. It is why serious papers now carry the requirement that every vacuum must decay faster than it can produce observers, which is a bizarre sentence to find in a physics journal, and it is standard. Some inflationary scenarios have been ruled out this way. Others have been rescued by showing they never had the problem. An idea that started as a footnote credited to an assistant and spent a century as a curiosity is now used to kill theories. And this is a decent moment to remember how new all of our looking is. We have had telescopes for about 400 years. Take the entire history of humans pointing a lens at the sky and set it against 14 billion years of universe. It does not register. Calling it a small fraction flatters it. Nobody would bother writing the fraction down.
Everything in this story, the acceleration, the horizon temperature, the Higgs, the map of 47 million galaxies, comes from a strip of observation so thin that if the history of the universe were a film, we have not seen a frame. We have seen a smear on the edge of one. We are making claims about eternity from inside a moment. That is not a criticism of anyone. It is the only position that has ever been available to us, but it should shape how tightly you hold any of it. Which brings the question back around, and it is not the question we started with. The question was never whether you are real. That framing is a distraction, and it is the one that gets clipped and posted and argued about, and it misses what is actually alarming here. The real question is why the past exists as a fact rather than as an assumption, why it is available to you at all. Rovelli has spent years on this, and his answer is uncomfortable in a way that is hard to shake off. You remember because you are a physical system sitting in a gradient. Memory is not a window, and it is not a recorder pointed backwards through time. It is a physical process that needs low entropy behind it and higher entropy ahead of it, and it runs in one direction only because the slope runs in one direction only. Every memory you have ever formed cost you something. You paid for it in heat. You have a past because the universe is running downhill and you happen to be standing on the hill. And now the awe that sits inside the fear because there is some and it is not a consolation prize. The only reason any of this is possible, the only reason there is a slope to stand on, is that 14 billion years ago the universe was in a state of absurdly, extravagantly low entropy. Not slightly low as anything we know how to describe. Every record, every fossil, every photograph, every memory you have of your own childhood is drawing on that one initial condition, still, right now, running on a reserve laid down before there were atoms. Nobody knows why it was like that. Nobody is about to fill that gap either. It remains the largest unexplained fact in physics, and it doubles as the single support holding up your certainty that yesterday happened. Everything you trust rests on something no one has been able to account for. Go back to where we started. You have a memory of yesterday. Somewhere near the beginning of this, I asked you to leave one memory in the comments. One you are completely certain is real. You will want it later, I said, and this is later. Look at it now. Nothing in this video has damaged that memory. No physicist thinks it is false. The sky over your house is full of stars, and the crude version of this argument fails that test outright.
By any standard a human being has ever used, the evidence that you have a real history is overwhelming. What has changed is smaller, and it does not go away when you close the tab. You made the choice about where to put your trust long before you knew there was a choice available, and everything you know got built on top of it afterwards. So there is one thing left worth asking, and I would rather you answered it than I did. You have to drive the nail somewhere. Everyone does. Where are you putting it? Into this moment, the one you are in, the only one you have ever had direct contact with? Or into the beginning, 14 billion years back, a moment no one has ever touched and no one can explain? Tell me in the comments which one you chose and why that one. Like the video if it earned it, subscribe if you want more of this, and if you are reading this at some ridiculous hour, put your phone down and go outside first. The stars are still there. For now, that is the whole answer.